Hey folks, well, last time we introduced the idea of parsing in general and talked about top-down versus bottom-up parsing. So today I want to start getting into some more detail on top-down parsing approaches. So again, the idea is that we're starting from the root non-terminal for our grammar, so whatever that starting point is our most abstract term, and then we want to successively go through and over again pick one of our non-terminals in the current state of our derivation and pick a derivation rule and apply it to that non-terminal, right? Arrive at a new sequence of non-terminals and tokens and gradually go through picking non-terminals and expanding them until eventually we arrive at a token string that matches the input sequence. If we get to a point where we can't go any further in our derivation and match the input sequence, then we back up and try an alternative path, try an alternative derivation in one of the choices that we made somewhere along the line. And if we run out of places where we can make a decision, where we can make a choice, then we have to eventually say, okay, well, I give up. It's not possible to get that token sequence from our grammar. So what we'll start with is just kind of a generic algorithm to go through and do this. So what we'll have is we'll keep track of the current non-terminal that we want to work with, or the current symbol that we want to work with, and we'll keep a stack of things that we still need to match. So in the beginning, this is going to be empty. And then what we'll do is, if the thing that we're currently working on is a non-terminal, then we'll try and pick a rule, one of the derivation rules, to apply to that one. So for instance, if we've got a rule that says our current goes to ABCD, then we'll replace current with ABCD, and the way we'll do it is by pushing them onto the stack as things that we have to match later, right? Pieces of our derivation sequence that the input sequence has to match, that the tokens have to match. So we'll push all of these elements on, and we're going to push them. The last thing to be matched goes on the bottom of the stack, and the first thing that we have to match goes on the top of the stack. So the idea is, if our grammar was simply, X goes to ABC, where ABC were all tokens, then I would have pushed C at the bottom of the stack, B on top of that, and A on top of that. And then what I'm looking to do is read through my token sequence, right? Read through the actual input sequence, see if the first thing in the input sequence is an A, and that matches the A that's on the top of the stack, and I can pop it off and throw it away. And then read the next character and see if it matches the B that's now on top of the stack, and match them and throw them away. So I'm going to be going through this process of either spotting tokens on the top of the stack that I can match with the next character in the input, or spotting non-terminals where I need to replace them with the right-hand side of a rule and push them on the stack. So this is where the algorithm's going. If current is a non-terminal, we'll pick one of the derivation rules for that non-terminal, push the stuff that it creates onto the stack, and pick the rightmost one of those things, or pardon me, the leftmost one of those things, as the new current element, right? The new thing that I want to process next. So that's if current is a non-terminal. If current is a token, then we'll see if it matches the next thing in, or the thing on top of the stack right now. And if so, we'll get rid of the top thing on the stack, it's been matched, and read the next character in our input sequence, or the next token in our input sequence, and keep processing. If anything goes wrong and we get to a point where we have a token in front that doesn't match the next token in the input, or if our current token doesn't match the next character in the input, the next token in the input, then we've made an incorrect decision somewhere along the line, and we'll backtrack to one of our recent decisions and try again. And if we get through all this and we wind up with an empty stack and we've read all our input, then everything's okay. We've found a sequence that matches exactly and we'll accept it. Otherwise, we'll reject it. So let's try that with an example to see if we can make a little bit of sense out of this. So let's say that the tokens in our language are A, B, C, D, E. So those are the things that ultimately our code has to, our source code has to be composed of. And our grammar rules, S will be our start non-terminal, and S can be an X followed by a Y, where an X can be either ABC or E and then X and an E, so that X could be expanded. So essentially, we could wind up with a whole bunch of pairs of E's on the outside and an ABC in the middle, right? So we could wind up with E, ABC, well, we could wind up with just ABC, or we could wind up with E, ABC, E, or 2 E's, ABC, 2 E's, or 3 E's, ABC, 3 E's. Right? That's what we can get out of this X. So that'll be the first half of whatever comes out of this. And then the second half is going to be our Y. Y can go either to a C followed by a Y or a D. So in this case, if we get a whole bunch of these things, then we could wind up with C, 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 and eventually we're going to wind up with a D. So what we've got is we've got an ABC somewhere on the left-hand side with matching E's around it, and then potentially a bunch of C's followed by a D on the right-hand side. So let's see if we can take a look at a string and try and come up with a derivation that matches it. So our string here is going to be our E, ABC, E, so you can see how that kind of came out of our X's, and then a CCD, and you can kind of see how that comes out of our Y's. But we'll see if we can come up with a derivation sequence that matches that. So we're going to work our way through the sequence and see what's happening in terms of the stack and our algorithm. So let me just bring up our rules so we've got those over on the side and we can follow them through. So we start off with our current is that start non-terminal, and we'll read the first character as our next token, right? So we'll keep track of what the next character in the input sequence is, and the rest of our input sequence, the stuff that's got to be processed later. Right? So we had E, A, B, C, E, C, C, D. So E is the first thing in line, and then there's all the rest. At the moment, we've got nothing on the stack, and we need to pick a rule, right? Current is a non-terminal, so we need to pick a rule to apply to S. Well, we've only got one rule for S, so that's easy. So we'll pick S goes to XY. So we push the Y on top of the stack, and in theory, we push the X on top of the stack on top of that, and then pop the X off and stick it in current. So what we wind up with is the Y on the stack, X in the current, and our token and input haven't changed. Right, so then we continue on to the next stage. Now we have to pick a rule for X and see what happens there. So let's say we pick, and I'm not going to give any rationale for this, let's just pick X, pick this rule for X where we're going to expand it to an EXE, and that kind of makes sense since the next token's an E. So we'll try that one. So again, we want to push the E onto the stack, push the X onto the stack, and then in theory, we could push the E onto the stack and then pop it into X, or just put it straight in X. So we wind up now with our E in X. The top of the stack looks like an XEY. And now we've got this terminal, this token E, and it actually matches the next token in our input. So we can say, we've matched the first of our tokens. Let's throw the E away and move on with the rest. So once we throw the E away, we pop the top thing off the stack to use that next. So now our current is X. We've thrown away the E, so the next thing in our input is A, and then we've got the B, C, E, blah, etc. to still process. And we've got, again, we've popped that X off, so the E and the Y are still on the stack. And we've got to figure out something to do with this X. So we pick a rule. Well, I can see that A is the next token in there, so I'm going to pick the rule X goes to ABC and see how that goes. So again, we'll push the C and the B on the stack, put the A in current, and now we've got A's in current. A's still our next token, and we've still got the rest of the stuff in the input stream. And we pushed the B and the C on the stack. So now our stack is B, C, E, and Y. And again, if we take a look, our token A matches our token A. So we've matched the second character in our input. We throw those away, pop the top thing off the stack into current, and read the next input character. So now we've got B is current. The B from here is our next character, and we've still got some other stuff to process. So this is a token, so we see if it matches the next token in our input string. Yes, it does. So again, we can throw them away, match them, pull the next thing off the top of the stack, which is our C, pull the next character from our input, which is a C, and again, we match them up. Hey, great, things look good. We match those, throw them away. So we'll pop that next E, or take that next E for our input and pop the next E for our current. And we just keep on going with this sequence. Again, E matches E, so great. We've just got C, C, and D left to deal with in the input, and we've just got a Y left on the stack, so we pop that Y into current. We read that next input character. And again, now we've got a non-terminal over here, so we have to pick a rule for Y. So I'm going to pick Y goes to CY, just because we've got a C coming up next. So in that case, we've got to push the Y and stick the C becomes our new current. So now we've got a C matches a C. Great, we can match them and throw them away. So we pop that Y into current. We read that next input character. So we're getting there, right? Again, we've got our non-terminal Y, we've got our character C, and then there's just one more character after that to process. Our stack's empty right now. So it makes sense to pick a C rule for our Y. So we say Y goes to CY, push the Y on the stack, and now we've got our C as our next current. Again, we get C matches C. Great, we can match them, throw them away. That D becomes our next input character. The Y becomes our next current. And again, this time it makes sense to replace our Y with the Y goes to D rule. So in this case, there's nothing else to push on the stack there. We get our D, and they match, and we throw them away. And yay, we've got an empty stack, or we've reached the end of our input. We've got an empty stack. We're good, and we can accept this particular string. So we've come up with a derivation. Now, if we wanted to record the derivation so that we could, figure out what it all meant later, then at each step of this derivation process, we could have printed which rule we were applying and which non-terminal we were applying it to. So we can get a very specific idea of what is taking place as our derivation goes along. All right. So, in fact, we mentioned that if our derivation goes wrong, we can back up and try something different. In fact, there are a lot of grammars where we can guarantee we can parse them without having to backtrack. And that's especially true if we allow the parser to look ahead at what character is or what token is coming up next in the input sequence. Remember in the example I was just going through there, I kept saying, oh, well, I can see that the next thing is a C or the next thing's an E, so I'm going to pick this rule. That's quite a common process where you go through and allow the next token to guide you in picking which derivation rule to apply next. So, for a lot of grammars, we can guarantee that we don't have to backtrack. There are a lot of circumstances where we can take the grammar that we're given and put it in a form that will be backtrack free. Now, this can't work for all grammars. There are some grammars that we can't make backtrack free in this form, but for the grammars that can't eliminate backtracking, we can still look at things that will reduce the cost associated with it. So we'll come back to that. So one of the big problems for us in applying a process like this is left recursion. So suppose we've got rules that look like we've got this non-terminal X can be replaced with that same non-terminal and then something else. One of the problems that we can run into in the derivation process is a case where we keep applying this rule. So I see an X and say, oh, I better replace that with X goes to X something. And so now, in the next stage of your derivation, you've still got an X in front, and you try and apply the same rule to that X. So now you've got an X something something. and you've still got an x in front, so you apply that rule again, and you've got an x something, something, something. And you get this kind of infinite cycle going on where you just keep applying that same rule over and over and over and over and over again, and you don't have a way to get out of that cycle. So this is called left recursion, where you've got this form of the non-terminal that you're applying next has as its leftmost symbol in the right-hand side the same terminal. So if x goes to x and then whatever else. So one of the things we want to do is to try and eliminate this. So this is called direct left recursion, where the symbol actually appears as the very first thing on the right-hand side of the rule. You can get the same effect even where it isn't direct like this, where you can go through a sequence of other derivation steps and wind up with the same behavior. So a nice simple example is to show this. Let's say we've got w goes to x, x goes to y goes to wz. So if you think about it, this x can go to y, this x can go to y, which can go to w. So, and then you've got the z afterwards. So this stuff in the middle is basically just a long way of getting you to the same point of saying w can go to wx. So this is where problems can arise with indirect left recursion. So again, you can have effectively through this process, w goes to wz, which goes to wwz, which goes to wwwz, etc., etc., etc. So ideally, we want to look for ways to get rid of direct left recursion and indirect left recursion. The direct is pretty easy. So if I've got something like this, where x can go to xb, so there's our direct left recursion, or it can go to a. So this is effectively describing, we can have a whole bunch of b's with an a in front, right? So we've got whatever's on the whatever's on the right-hand side here can get repeated over and over and over again, and then this is going to wind up on the left-hand side. So we can wind up with a sort of AB star is what this is really describing. So what we'll do is take this rule and replace it with a new pair of rules. So we'll say instead that x can go directly to an A, followed by our new non-terminal n, and we'll say that that n can go to nil, and that's how we can guarantee that we get that A on the end. Or our second rule will be that this n that we introduced can go to a b followed by an n. So this is where we get the sequence of b's, but we're generating them from left to right instead of from right to left, if you like. So this way, every time we apply this rule, we're actually matching a new token, and then the continuation of the rule is afterwards. So this lets us break that cycle where we can't have this left recursion, and we don't have indirect left recursion introduced by this either. So we've introduced a new non-terminal that can go to nil and rewritten things so that the tokens appear on the left-hand side rather than on the right-hand side. So that's how this is working. Now, for indirect left recursion, it gets a little bit uglier. Because, again, we have to account for all the cases where we've got this kind of sequence of steps in between before we get back to our original token, our original non-terminal. So what we're going to do is apply just an arbitrary ordering. I'm going to say, okay, my non-terminals are going to be numbered 1, 2, 3, 4, 5, 6, 7, whatever order you like. And then we'll go through each of them in sequence, and for whatever non-terminal we're looking at right now, I'll look at all of the ones that come before it in the sequence and see if my ni has a reference back to one of the earlier ones. And if it does, then that's one of the places where we can get this indirect left recursion coming up. So that's one of the things that we want to replace. And so what we'll do is we'll look at all the things that the earlier one can go to, the nj in this case, look at all of the things that it can go to, and have ni go directly to them instead. So if we used to have a rule that says ni can go to this earlier nj followed by an x, and we know that nj can go to y, for instance, then we'll introduce instead a new rule that says ni can go to the y followed by the x. And again, there might be a whole bunch of things like this, a whole bunch of different things that nj can go to. So we'll introduce all of them as potential options for ni to go to. So we'll just build this up in sequence, guaranteeing that any time there's a backwards reference, we replace it with a structure like this. So what this will eventually do is drive us to a case where the thing on the first element on the right-hand side of our rule is going to be one of our ni's. If indirect left recursion actually exists, eventually this is going to push us back to something that looks like ni goes to ni blah 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 blah. At that point, we've seen direct left recursion and we know how to replace that easily. So this can introduce a whole lot of new rules, so we very much want to automate this and not try and do it by hand, but this is the cycle that we go through. Right? We get it to go through, replace all of the backwards references, if you like, with new sets of grammar rules, and then any place where one of those actually is direct left recursion, we apply our direct left recursion rules to get rid of those. All right, so we can go through and get rid of this. What we're going to get into next are the sort of predictive grammars where we can look ahead and produce a backtrack-free approach to parsing anything in the language. So with these predictive grammars, when you're picking a rule, you get to look at the next input token, select from just the rules that can apply with that next token, and if we can come up with one of those that's backtrack-free, then we can come up with a really efficient parsing algorithm recursively. And that's where we're going to go next, recursive top-down parsers. Now, again, unfortunately, not all grammars will work with this, but a lot of grammars will, and for those, we can come up with very efficient recursive parsers for them. All right, I will leave it there for now, and we'll get into the top-down recursive parsers next time.